So starting with something super easy, the area of that rectangle, yes, is base times height, or length times height, or base times width, or however you wanted the two dimensions. And for this one, it's width times height. We know that. Riemann sums, people get all confused and think that it's difficult, and they convince themselves that it's hard, when really it is just adding areas. And in some sense, I hope we finished today and you're like, wow, we spent 30 minutes, 40 minutes talking about adding areas. Yep, that's all it is. So don't lose sight of that. There's going to be calculus symbols and there's going to be different areas to add. But at the end of the day, the whole day today is just adding areas. Mostly rectangles, but not all rectangles. Okay, so first the motivation. We would like to be able to find the area under the curve from A to B. And so you look at those four graphs down there and they all look the same. We're going to do different stuff with them. But that means we want to find the area under that curve, which would be kind of tricky to do because that's not a standard looking shape that we know. So we use Riemann sum approximations. So this won't tell us it exactly. And use rectangles to approximate the area under the curve. We use rectangles because rectangles are easy. That's really the reason. We could squeeze some rectangles in there and get a close approximation, and finding areas of rectangles is easy, so let's do it that way. And so the guy that came up with this seems pretty basic, but he gets credit. Bernhard Riemann, Riemann sums. Okay, in this first picture, let's draw rectangles using the left side of each rectangle as the height of the rectangle. So I think what we'll do first is let's divide it into, it doesn't really matter how many divisions you have. So divide it into intervals there. Preferably equal intervals, but they won't always be equal intervals, so it makes your life a little easier if they are equal intervals though. Okay, so a left sum comes from the left side. We're not trying to be confusing in our naming here. So in this first interval, I'm going to come from this side, the left side of that interval, and this would be my area for my left sum. On the next interval, we come from the left-hand side, and we use that area. And from the next interval, we come from the left-hand side, and we would use that area. And we can see already with just these first three that some of our rectangles are below the curve, like this first one. So like entirely below the curve. Some are entirely above the curve, like this last one. Some are pretty close to being a pretty good approximation, like that middle one. Let's keep going. So coming from the left, there's another one that's above the curve, followed by one that's below the curve, another one below the curve, and another one below the curve. And so that, if we added up all those areas, we would get an approximation for the total area. And it kind of just depends on a number of things, like how good our approximation is. We're not worried right now about how good the approximation is. We'll worry about that later. All right, let's draw right rectangles. So let's kind of do the same thing. Let's put in some intervals. Divide up the area into intervals. And if we want a right Riemann sum, we should use the right side of each rectangle. Here's where people do this a little bit differently in terms of what they draw. It's the same answer. I've always done it like moving left to right. So on my first rectangle, I'll come from the right, and there's my right rectangle. what some students do, it makes more sense to them, is they start all the way on the far right-hand side and come from the right like that. Which is equally okay because you're still coming from the right-hand side of the rectangle. It's just, if you're coming from the right, some people want to start all the way at the right. Other people want to work left to right on the rectangle but still come from the right-hand side. It doesn't matter. By the end of the process, we'll all have the same rectangles drawn. And again, some are above, some are below, some are pretty close. And you figure if there's enough rectangles, it's maybe a good enough approximation, depending on what you're trying to find and how important it is. But the right sums come from the right-hand side. And the left sums come from the left-hand side. It's hard to draw it because once it's drawn, it's all right. Well, someone maybe came up with the idea of, well, what if we did? You know what? Let's divide it into our areas or our intervals again. So someone else might think, well, the left sum, the right sum, maybe those are accurate, maybe not, but what if we just did the midpoint? So for each interval, look at the midpoint, grab the height at the midpoint. That's a better way to say that. The height at the midpoint of the interval. 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 This feels like it would be more accurate than the left or the right. But you can't say it for sure, so you have to be careful about that. It certainly feels like it would be, because at every one, it's like my first interval, that looks like a pretty good rectangle because it's got some area above, but it's missing some up here. So if I took that little bit of triangle and put it right there, like this, that rectangle's probably pretty good. The next one's pretty good. The next one's pretty good because above and below. So it just feels like midpoint would be a little bit better than left or right. And again, we're not too concerned with accuracy yet. Well, someone else said, well, what about a trapezoid? Because that would really match better. So let's put in our intervals again. And these are almost hard to see because a trapezoid, you just connect the endpoints. And so this is going to trace the curve really well. Again, sometimes this looks like you're right on the curve. You can't even tell that you put a trapezoid in there. You're just connecting the dots. Obviously, it's still not perfect. You still have some trapezoids that are outside or above the area and some that are inside the area. So it's not perfect. But man, that sure looks like a good approximation. because it just tracks along with our curve pretty well. Here's the geometry we need this lesson today. The area of a rectangle is height times base, or base times height. The area of a trapezoid is the average of the heights. So like h1 plus h2 over 2 times the base. Average of the height times the base. So it's kind of like a rectangle formula. Instead of height times base, it's average height times base. Okay, now we start transitioning into calculus a little bit and putting a little more math behind just drawing pictures. The area of a rectangle is base times height, or height times base, right? So that's the same thing. Each height is the function value at each x value. So you can phrase it this way: the height is the function at whatever x value you're at, f of x. And it might be the x on the left or the x on the right, but the height is f of that x. And each base is delta x. It means change in x. And then the area is just the sum of all the rectangles. So we start building a math formula here. The sum of the area of each rectangle is the sum of each height times each base. Right? Because height times base is the area. Height is f of x, base is delta x. And so we start heading toward a more mathy looking formula. But that mathy looking formula still just means add all the rectangles. Okay, so don't get lost in the, I don't know what the big capital E looking thing means, and f of x and delta x. It's all fancy words and fancy symbols for add all the rectangles. Now, we mentioned being more accurate or getting a better approximation earlier. And probably the best way to get a better approximation is if you let the number of rectangles go to infinity. Now, it would be very hard to add up, an infinite number of rectangles. But certainly you could say, looking at that picture, I drew 7 rectangles. If you drew 8, you'd be more accurate than me. If you drew 100 in there, you'd be really accurate. If you drew 200, you almost wouldn't be able to draw them in there. They'd be so accurate. So if we let the number of rectangles go to infinity, we get Leibniz notation for integrals. That capital E thing, which symbolizes sum, because really that's a Greek sigma for s, it turns into the symbol for integration. I think we talked about this maybe briefly. S for sum, if we stretch it out a little bit, and then stretch it out some more, and then stretch it out a lot, that's where that symbol comes from. So the first time you see it, you're not thinking S, but that's where it came from, is it's a stretched out S. It's the sum. It means the sum. So that big capital sigma turns into a sum, and the delta x turns into a dx. Delta x is like a finite width. Dx means it's just really small. So it's the same width in the x direction, but dx is if the width is super small. The boundaries on the integral, we haven't had boundaries on integrals yet, so we don't really know what that means. We looked at that as an antiderivative, but now you're looking at it as a sum of rectangles. And so that's weird that those are the same thing, but that's more to come on that. So the boundaries of the x values are a and b, so from bottom to top, from a to b. So this is a different way to write the area under that curve. So from a to b, add up all of the y values, that's what f of x is, times dx, that's the width. So the y values, that's like a dash there. The y values times the width, that's the area of each little rectangle. And if you add up all the rectangles, you get the total area. Now, we're not going to make this connection just yet. We're going to stick with doing approximations. We can approximate that area. In fact, we should say that is the exact area under the curve. If you do it that way, that is the exact area under the curve. But we don't know how to do that yet. We don't know how to add up an infinite number of rectangles. That didn't quite make sense. So for now, we're going to approximate the area with a finite number of rectangles. So some left rectangles, some right rectangles, some midpoint rectangles, and even some trapezoids. Okay, I think that half of the page is the most confusing part. Actually, doing the problems isn't really that bad because all we're doing is adding rectangles. Okay, so don't get lost in the symbols. We're adding rectangles or trapezoids, so be careful. So height times base, or average height times base. Number 1, let f of x be a continuous function. Selected values are given in the table above. Estimate, okay, this means the area, let's see what this means here, the area under f of x from 0 to 140. That's what that statement means. It's just a whole lot easier to write that integral than it is to write out all the words. So we're going to estimate the area under the curve from 0 to 140 using a left sum and 5 subintervals. Okay, so here's my x values. So you can almost view this as like it's almost my xy axis there. So I've got a rectangle going from 0 to 20, and a rectangle from 20 to 50, and a rectangle from 50 to 70, and 70 to 100, and 100 to 140. I don't really know how tall those are, but it doesn't matter. Okay, so I'm going to just add up the rectangles. So here's my first rectangle going from 0 to 20. So how wide is the rectangle? If it goes from x equals 0 to x equals 20, 20. And if I want to use the left sum on my, I'm just looking at 0 to 20 now, the height at 0 is 100, the height at 20 is 90, but if I want a left sum, which height should I use? The 100. Why? It's the one on the left. So 20 times 100. That's my first rectangle. Now be careful, and like this seems like oversimplifying to do what I'm doing, but it helps me like visualize and see what I'm looking at here. So my next rectangle goes from 20 to 50. How wide is that rectangle? 30. And which height should I use? 90, because that's the one on the left. And then from 50 to 70, how wide? 20. And which height should I use? No, 80. It kind of doesn't matter because they're both 80. But I'm using this 80 because it's the one on the left. Using the left 80. And then, lost track of where I was. So 0 to 20, 20 to 50, 50 to 70, 70 to 100. How wide is it from 70 to 100? 30. And which height should I use? The 80, because that's the one on the left. And then 100 to 140, the width. How wide are we from 100 to 140? How wide is that rectangle? 40, and which height should I use? 90, because it's the one on the left. AP College Board, they need to see this stuff written out. They have to see that written out. Once you've done some of these, you'd be able to just type them in your calculator, because you'll just be like, okay, look, it's 20 times 100, it's 30 times 90, 20 times 80, so it's not hard to type it in your calculator. But the AP grader, me included, I need to see that you understand what you're doing, that you're multiplying a width times a height, the width times a height, the width times a height. In fact, it's probably better to leave it like that and only simplify for multiple choice. Right? Like, that's a safe stop. And it's a great safe stop because I can easily see what you've done, and you've clearly communicated that you knew what was going on. So if you want to simplify, fine, but I must see that line where you've written out base times height plus base times height plus base times height. Part B, estimate 0 to 140 f of x dx. Okay, well, all of that means the same thing we just said it did. That's the area from 0 to 140 under the curve. But this time we're using a right Riemann sum. All right, so our intervals are the same. So I'm going to say area approximately equals. Maybe I should put all this down. The integral from 0 to 140 f of x dx. That is the area, and it's going to approximately equal the right rectangles. So same process. How wide is the rectangle from 0 to 20? 20. And what height should we use? 90, because that's the one on the right. Why don't you see if you can finish that problem? For a trapezoid, it's width times average height. So from 20 to 50, my width is 30, and the average height is 90 and 80, so 90 plus 80 over 2. And then from 50 to 70, that width is 20. And this looks like a little overkill to write 80 plus 80 over 2, but you're emphasizing that you're doing the average height. And then 70 to 100 is width of 30. 80 plus 90 over 2. And that last one is a width of 40. And the two heights, 90 plus 130 over 2. And you maybe go back and check. I thought there was 5 of them, 5 intervals. 1, 2, 3, 4, 5. So I'll make sure I have 5 terms here. 1, 2, 3, 4, 5. So I feel pretty good about my trapezoids. And again, I'm not even going to simplify that because that is a safe stop. So why risk making some mistake? Just leave it alone. Part D. Given that f double prime is greater than 0, what's that mean in terms of the graph? If the second derivative is positive, what does that tell us? Or concave up is the approximation found in part C. So that means the trapezoids. An overestimate or an underestimate. Okay, well, let's draw something that's concave up. And then let's think about what it would look like to put trapezoids on there. And it's best to spread them way out if you really want to see if it's an overestimate or an underestimate. So my trapezoids So what do you think? Overestimate or underestimate? Over, because the trapezoids are overlapping or bigger than the curve. So since f double prime is positive, a trapezoid sum is an overestimate. That's one of those things where you don't memorize that. I mean, yeah, it's true, and that would mean that f double prime is negative, the trapezoids would be an underestimate, but you don't memorize all those different combinations of things. You just sketch a picture of what it says, and then you can use the picture to figure out what it's asking. Right? We're going for understanding, not memorization. Number 2. Let h be a continuous function. Selected values of h of t are given in the table above. Estimate from 30 to 90 the area under the curve using a midpoint sum and 3 subintervals. Okay, let's be careful. I want 3 subintervals. So that means I need to skip over one. So I'll go from 30 to 50, 50 to 70, 70 to 90. That gets me 3 subintervals. And so my delta x on the first one, 30 to 50 is 20. Second one, 50 to 70 is 20. And on that last one, 70 to 90 is 20. So they're equally spaced. So 30 to 90, h of t dt, that means the area is going to be approximated by my midpoint rectangles. So my width is 20, and then what height should I use for that first rectangle? I got 3 options now. What do you think? Why 7? It's the middle one, right? That's why it's called the midpoint sum, is because we'll use the midpoint heights. So 20 times 7, we'll use the midpoint sum. For my next rectangle, my width is 20. What height should we use? Which one's in the middle? 15. And then for my last rectangle, my width is still 20 from 70 to 90, and I'll use the middle height of 16. Once you get the hang of these, it's not hard, but you got to read carefully to know like which height to use. And this one, it feels like you have more information because it looked like before you got the question prompt, it looked like, okay, we're going to have a bunch of rectangles, but because it was a midpoint sum, they only wanted 3 rectangles, and we used that midpoint as the height. All right, number 3. Approximate the area. So remember, this means the area from 0 to 2 under negative x cubed plus 2x squared plus 1 using a left Riemann sum and 4 equal subintervals. So I don't have the values for my heights. Let's worry about the 4 equal subintervals first. So if I'm going from 0 to 2, I'm going from 0 to 2, and I want 4 equal subintervals, how wide are my subintervals going to be? Again, no formula. You just got to look and figure things out. Width of the subinterval. Width of the subinterval. Well, the total width is 2, and I want 4 of them. So yeah, they should be half. So there's my subintervals. Each be a half wide. So I'm going to need, if I want my left Riemann sums, I'll need the height at the left. Height at the left hand, height of the left side of the subinterval. So I'll need the height at 0. I'll need the height at 1/2. I'll need the height at 1. And I'll need the height at 3/2. Does that make sense? Do you know why I'm finding f of 0, f of 1/2, f of 1? Why am I not finding f of 2? Because that's on the right. That's the right-hand side of a rectangle. So I won't need f of 2. I only need f of 0, f of 1/2, f of 1, and f of 3/2. Okay, so let's plug in 0. That's an easy one. Get 1. If I plug in 1/2, this is kind of annoying. Hope your algebra is quick and good. 1/2 cubed is 1/8 with a negative on there. Plus 2 times a fourth would be 1/2 plus 1. Let's see, so if we put all of those over 8, that would be negative 1/8 plus 4/8 plus 8/8. That would be 11/8. This is one of those places where, the hardest part of calculus is the first 12 years. If you struggle to add fractions, then you're going to get bogged down. If I plug in 1, I get negative 1 plus 2 plus 1. So that would be 2. I plug in 3/2. Let's see, that's negative 27/8 plus, let's see, 9/4 times 2 would be 9/2 plus 1. Common denominator would again be 8. So negative 27 plus, multiply top and bottom by 4. So that'd be 36 over 8 plus 8/8. 36 minus 27 is 9. 9 plus 8 is 17. 17/8. There's going to be a handful of people in each class who miss this problem because they can't plug in numbers and do the arithmetic, and that's frustrating. I need another stamp that says calculus is easy, arithmetic is hard. Okay, so I've got my heights. My area then is width times height. So my first width is 1/2. Actually, all my widths are 1/2. 1/2 times 1. That would be this one. And then my next one would be 1/2, because they're all 1/2, times the height at 1/2, but that would be 11/8. And I don't know if I'm drawing these to scale or not. I'm just trying to keep track of which rectangle I'm on. Plus the width is 1/2, and the height is f of 1, which is 2. And then lastly, the width is 1/2, and the height is f of 3/2, which is 17/8. And again, safe stop, so I'm not messing with that. That's my answer. Again, hardest part of calculus is the first 12 years. That's a great example of that. By the way, so that adds up to, if we got a calculator or get all the common denominators, 13/4. So our approximation is 13/4. The real area is 3.333 repeating. Let's see, 13/4 is 3.25. So that's pretty good. I mean, we only did 4 rectangles, so it feels like that's probably not all that accurate. And yet, we got 3.25, and the real number is 3.33. So that's pretty good. Obviously, if we did 8 rectangles, we'd be even better. And Once we figure out how to do infinite rectangles, we'll be perfect. But even with 4 rectangles, that's pretty close. All right, last one. The amount of water in a draining tank is given by a strictly decreasing function where W is given in the table below. Use a Wright-Riemann sum with 4 subintervals. That makes sense because look, there's 4 intervals to be had to approximate the area under the curve from 0 to 40. So this has some words on it, but it's kind of the same thing. Do a Wright-Riemann sum. Whoops, I'm going to put approximate because we're using rectangles rather than actual area. Why don't you try that one? There's the right rectangles. If you're decreasing and coming from the right, you're always under the curve, so underestimate.